Alright, so far we've been playing around a lot with polynomial functions and learning some new things. So far we have talked about symmetry, we've talked about extrema, local and absolute. In the last module we talked about end behavior and the relationship between the number of zeros and the number of turning points and the degree. In this section, we're going to talk about finding the real zeros, and we're actually going to get back into doing some math. All right, so let's go ahead and get started. Okay, so this is nothing new, okay, but what we have is we're going to start by reviewing what are zeros of a polynomial function. So remember that a zero of a polynomial function is where the function f of x is equal to 0. When we talk about finding zeros of the polynomial function algebraically, we want to set the function equal to 0, and we can either use factoring or quadratic formula to solve. Now, in the previous modules that we've looked at, remember that we can also talk about zeros graphically. And when we look at the zeros graphically, we are looking for the x-intercepts. And remember that we keep only the x-coordinate. Now, furthermore, we can talk about zeros in function notation. And so if we have a number k, and it is 0 of f of x, then what this means is that when we plug in k to our function, we should get that the function is equal to 0. Finally, the last thing we have is if we are looking at tables. To find zeros using a table, we identify and keep the x values that have a 0 in the y column. Okay, so the main thing that we're seeing here again is notice that we have lots of different ways to ask the same question. We have lots of different ways to denote our answer, and so we're just going to go ahead and kind of focus on this in this first couple examples. All right, the thing that we do want to talk about is something new, and it's technically not new. We've been playing around with it for quite a while, but we have something called the zero factor theorem. And the zero factor theorem says that if you have a polynomial and that x minus k is a factor, if and only if f of k is equal to 0. This goes back to how do we solve algebraically? Well, we set it equal to 0, we factor, we set each factor equal to 0, and we get x equals k. And so when we say x equals k, we can also say x minus k is a factor, and so these are all synonymous statements. So this is what we're going to play around with. We have number 1, and again, they all mean the same thing. The first one we have, k is a 0 of f of x. The second statement we have is x minus k is a factor of f of x. This is also the same as saying k comma 0 is an x-intercept for f of x. And finally, f of k is equal to 0. Okay, so all of these mean the same thing. The one thing that I do want to point out is notice that all of these we have k is a 0, k comma 0 is an x-intercept, f of k equals 0. But notice that when we talk about it in factored form, that our sign is different. And that's the main thing that we do want to focus on, is that when we go from just a number to a factor, we change the sign. Just like when we go from a factor to a number, remember to solve for x, we have to move that number over to the other side and we change the sign. All right, so in this section, we're going to go back and forth between finding zeros given an equation or a graph and creating an equation given a graph or zeros. All right, so let's go ahead and practice going between these different notations before we get into real problems. All right, let's start with our first example. Our first example, we are going to start with a graph, and we want to identify the x-intercepts. We've done this before. So when we look at our x-intercepts, we have an x-intercept of -1, comma 0. We have an x-intercept of 0, 0. We have an x-intercept of 1, 0. And we also have an x-intercept of 3, 0. All right, the second thing that we want is we want to know what are the zeros of the function. And remember that the primary difference between x-intercepts and zeros is we only keep the x-coordinates. And so up here, we're going to keep the -1, this 0, 1, and 3. And those will be our answers. All right, we also want to write these points in function notation. So remember function notation, we put our x-coordinate inside the parentheses, and our y-coordinate goes on the other side of the equal sign. So for instance, the first one, f of -1 equals 0. Second one, if we plug in 0 for x, we get 0. The third one, when we plug in 1 for x, we get 0. And finally, if we plug in 3 for x, we get 0. All right, the next thing we want is we want this function in factored form. So I'm going to go back to my zeros, and I'm going to bring them down here. And remember that when we write these as factors, we change the signs. So for instance, if we have x equals -1, this is a factor of x plus 1. What we're doing is we are moving this number back over here with our x. All right, we have x equals 0. Well, okay, that's just x. We have x equals 1. That becomes x minus 1. And when we have x equals 3, that becomes x minus 3. So again, when we move each one of these numbers over with the variable, we do have to add it if it's negative, subtract it if it's positive, and then we get this. This looks kind of weird because of that x kind of in the middle. And so I'm going to move the x to the front. It does not matter what order you write this in, as long as these are our 4 factors. The last thing that we do want is it does say the function And so right now I just have an expression. We do want this as a function, and so we're going to say f of x equals x times x plus 1 times x minus 3. It asks for it in factored form, and you're going to find that as we progress through a lot of these topics, we always like leaving things in factored form. It's easier to see what's going on with our graph. And so this is our final answer. All right, the last main thing that we need to talk about when we talk about polynomials is we're going to talk about zeros with multiplicity. When we look at a polynomial in factored form, we have factors. And a multiplicity just refers to the number of times a factor appears. And this is represented by the exponent. If you think back to our quadratics, remember that we had factors that, we could have x plus 1 and x minus 3. We could have things that didn't factor entirely and didn't have any x-intercepts. But we also had a case where, for instance, if we had a factor that repeated like x plus 1 times x plus 1, well, we only had one zero. It came down and it basically just touched the x-axis at that point. And the reason is because it had a multiplicity of 2. And so when we talk about multiplicity, we're going to talk about, a couple different things that can happen. Multiplicity affects what the graph looks like at its corresponding x-intercept. If it has an odd multiplicity, what we're going to see is it crosses through the x-axis. Think about all your linear functions. Think about the quadratics where we had 2 x-intercepts, all of these things, okay? And so for odd multiplicity, we're going to have one of two things. If it has a multiplicity of 1, if you zoom in, it's going to look like a line. On the other hand, if it has a multiplicity of 3, 5, or any other odd number, when you zoom in, it will look like a cubic or a fifth power or something else. Okay, so just a reminder, what we're talking about when we mention these is, for instance, if we have a multiplicity of, if a factor has a multiplicity of 1, when we zoom in, it's basically going to look like a line near that x-intercept. On the other hand, remember that our cubic and our fifth power and all the other ones, when we talked about the basic ones, what they had a tendency to do is they came in, they got shallow, and then they took off again. And so if you have something that looks like this, then it's going to be an odd multiplicity, and it's going to be more than 1. All right. Now, we also have zeros with even multiplicity. And so when we talk about even multiplicity, what it does is it will touch the x-axis. If it has a multiplicity of 2 and you zoom in, it will look like a parabola. On the other hand, if it has a higher even multiplicity, 4, 6, etc., then it's going to look like a fourth power, sixth power, etc. And so what's the difference between the two? Well, when we talk about a x squared has a tendency to have that U shape, like that. But remember that for fourth powers and higher powers, what we see is that it gets steep on the outside and it has kind of like a little level spot in the middle. And so it's going to look a little bit more flatter on the bottom and then increasing a lot more on the sides. All right. This is what we're going to be working with in this section, is we're going to talk about zeros. And the main things that we do want to focus on here is we are going to be focusing on these terms of crossing the x-axis and touching the x-axis. All right, let's go ahead and look at some examples. All right, let's go ahead and look at some examples. For each one of these problems, we want to determine the zeros and we want to identify their multiplicity. After that, we do want to write an equation in factored form. So let's start with our first one. Our first one, we have zeros. We have x-intercepts. We have an x-intercept at -2, 0. And we have an x-intercept, comma 0. All right, so our zeros, remember that when we talk about the zeros, we just keep the x coordinates. We have a 0 of -2, and we have a 0 at 6. We want to know their multiplicity. All right, when we look at the first one, and again, we just want to zoom in on it. When we look at -2, if I zoom in on -2, it looks like a line. And so what this means is that just like all lines, this is going to be a multiplicity of 1. However, when we look at x equals 6, if we zoom in, this looks like a quadratic. And so this one, we're going to go ahead and say has a multiplicity of 2. All right, so when we write this in factored form, we're going to take each zero, we're going to write it in factored form. So x equals -2, this is going to become a factor of x plus 2. The 0 x equals 6, we are going to turn it into a factor of x minus 6. And then we want to bring in our multiplicities. And so remember, multiplicities is how many times do these factors occur. Because x equals -2 has a multiplicity of 1, we just have it as a factor. We just have one factor. For x equals 6, we have a multiplicity of 2, which means that I want this factor to appear twice. And we're going to represent this using an exponent. The last thing that we want is, we do want to check, is this function, we're going to leave it like this, but do we have the correct end behavior? Well, let's see what we have here. Okay, let's just kind of do some checking. Let's review some of the things that we've talked about previously. Right now, when I look at my degree of this function, degree is also equal to the number of factors. And so here, when we look at this, I have 1, and this factor appears twice, so that's going to be a degree of 3. Does it have 2 turning points? And we do have 2 turning points. We have one down here, and we have one there. The last thing we want to know is end behavior. Remember that end behavior, what we want is we want it to be going up on the left and down on the right. But that's not what I have here. Remember that in order for it to go up on the left and down on the right, we need our leading coefficient to be negative. Okay, well, it's very easy to do this. All we have to do is add a negative in here. And it doesn't affect our zeros at all. All it affects is this negative on the outside just reflects our graph across the x-axis. And then now we have what we want. All right, that's the first one. Let's keep looking at some more and get some more practice. All right, let's go ahead and look at our second one. All right, we're going to start by finding our x-intercepts. We have x-intercepts at -3, which means that our zeros are going to be -3. We have a 0 at -1, 0, or an x-intercept at -1, 0. And so we have a 0 of -1. And then we have an x-intercept at 2, 0, which is a 0 of 2. All right, for each 0, we want to know what is the multiplicity. And so our multiplicity for -3 is going to be 1. It crosses through the x-axis. And when it crosses through the x-axis, it looks like a line. At -1, it also crosses through the x-axis. It also, if we zoom in close, looks like a line. And so that has a multiplicity of 1. And finally, at x equals 2, we are touching the x-axis. And so remember, this has an even multiplicity. And we're going to go with a multiplicity of 2. If we zoom in real close, it will look like a quadratic. All right, we're going to go ahead and write our function. Remember that we're going to rewrite each one of these zeros as a factor, and we want to change the sign. So x equals -3 is going to become x plus 3. Because it has a multiplicity of 1, we're just going to have just one factor. For x equals -1, we're going to change the sign and turn it into a factor of x plus 1. Similarly, we have a multiplicity of 1, and so we'll leave it like this. And then finally, our x plus 2, I'm going to rewrite it as x minus 2. It has a multiplicity of 2, and so we're going to write this as x minus 2 squared. All right, the last thing that we want to do is we want to go ahead and just check for our leading coefficient. Do we have it correct? And so for this, we're going to go ahead and look at what we've got here. All right, we have 4 factors total. We have 1, 1, and 2 more. That makes 4 factors. And so we are looking at a degree of 4. All right, the last thing, or the next thing that we have is, do we have turning points? How many turning points do we have? Well, for this above example, we have 3 turning points. We have one up here at the top, one down here at the bottom, and again that one on the x-axis. And so that does support a degree of 4. Now, degree of 4, remember that if we are degree 4, and we are opening down and down, what this means is I need a negative leading coefficient. And so we are going to go ahead and change this to a negative. All right, that takes care of this one. Let's look at a couple more. All right, let's go ahead and look at the third one. All right, the third one, we want to start by finding our x-intercepts. We have an x-intercept at -4, which means that we have a 0 of x equals -4. We also have an x-intercept at 2, or at 2, 0, which means that we have a 0 of 2. All right, for both of these, we do have that it crosses the x-axis. When we look at -4, notice that we're above it, and on the other side of -4, we're below it. Similarly, for x equals 2, it does cross, but notice that this one does not look linear. If we look at it here, we're coming up, we're shallowing out, and then we're taking off again. So even though it does have an odd multiplicity, it's not going to be 1. So let's talk about our multiplicities. The first one, -4, it does have a multiplicity of 1. It basically goes straight through the x-intercept. At 2, it is going to be an odd multiplicity because we do cross, but we want something larger than 1. I want an odd number larger than 1, and so we're going to go with 3. All right, from here, we want to go ahead and create our function. Because x equals -4 is a 0, we know that x plus 4 is a factor. It has a multiplicity of 1, which means I just want one factor, and so we don't have to do anything with this. For x equals 2, if x equals 2, then that means x minus 2 is a factor. Has a multiplicity of 3, and so we are going to go ahead and put an exponent of 3. All right, so here, when we look at our degree, we have a total of 4 factors, including the x minus 2 cubed. And so our degree is going to be 4. And we want an end behavior because our degree is when we look at our end behavior, we are going up and up, which means that my leading coefficient is positive. And so we don't need to do anything else with this one. All right, let's go ahead and continue on. All right, we are on our last example. All right, this one's going to be kind of the most complicated, but let's go ahead and talk through it. Okay, we want to start by finding our x-intercepts. All right, our axes, our tick marks are increasing by 2. And so my zeros, we're going to have x equals -8. We also have one right here, so that's going to be x equals -4. And we have one right here, which is x equals 2. Okay, for x equals -8, we touch the x-axis, which means that my multiplicity is going to be even. I'm going to come back to this in a minute. And for the other ones, we do cross. Now when I look at this, I'm going to start with the -4. And when I look at the -4, to me is we are not going to have a multiplicity of 1. We basically come up, we level out, and then we take off again. And so it is going to be an odd multiplicity, and I'm going to go with a multiplicity of 3. All right, the second one that I'm going to look at is x equals 2. It has the same basic shape. It is going to be an odd multiplicity because it does come down, it levels off, and then it takes off again. But notice here that this one is coming in at a much sharper angle, and it's taking off at a much sharper angle. And so to me, when I see that, I'm thinking that I want a multiplicity that is odd, and I also want it to be larger than 3. And so I'm going to go with 5. All right, the last one I'm going to look at is -8. We are touching. We do want an even multiplicity. But notice that this is also sharper than our x cubed. And so for me personally, I'm thinking I want to go with a multiplicity of 4. Technically, for all of these, when we're trying to create an equation, you can always go ahead and go squared or cubed. The main thing that I'm looking for is not did you get the exact right multiplicity, but do you recognize that it is odd or even? All right, we're going to go ahead and set up our function now. All right, the first one that we have is we have x equals -8. When we write that as a factor, we're going to turn it into x plus 8, and we're going to say it has a degree of 4. Our second x-intercept, we have x equals -4. We're going to turn that into a factor of x plus 4 with an exponent of 3. And my last one is going to be x minus 2. We have x equals 2. As a factor, that's going to be x minus 2. And we're going to raise it to the 5th power. All right, when we look at our degree, we want to add our exponents. And so we have 4, 3, and 5. That is a total of 12 factors. If we multiplied this out, we would have a degree of 12. We're not going to multiply it out because this is not fun. All right, we got a degree of 12. When we look at our end behavior, we do have it as an even degree, and we do have that it is going down and down, which is one of our possibilities for a degree of 12. And so what this tells me is I do want my leading coefficient to be negative. And this is what we end up with. All right, now technically, we are still missing one thing, and it's not something that I'm going to focus on in here. And the problem is, if you do plug in 0 right now, you are not going to get an x and a y-intercept that is around 12 or 13. This is something that we will discuss in future math classes. For right now, I really just want you to focus on the factors, the multiplicity and their exponents, and the leading coefficient, is it positive or negative. All right, that takes care of our graphing examples and going from graph to equation. All right, we're going to go ahead and continue on to another topic. All right, the next thing that we're going to talk about is completely factored form. We want to start with a polynomial that is written in descending order. And the first thing that we want is that all of our zeros, or it has n real zeros, where a distinct zero is listed as many times as its multiplicity. Basically what it means is that instead of writing a factor raised to the third power, we write it out 3 times. And so what we have is, this means that f of x can be written in completely factored form. What we're going to have is we are going to have a leading coefficient on the outside, and then each one of our zeros written as factors. Now, one of the things I do want to point out is that if we have a 0 that is a fraction, what we can do is write the factor as bx minus a. Just to show, and it's just mostly to make it a little bit easier to look at, so that we don't have fractions running around. And so just to show you why is this, if we start off with a factor of bx minus a, in order to solve for x, we add a to both sides, and then we divide by b. And so if we want to work backwards, let's say we start with x equals a over b. I can multiply both sides by b to get bx equals a. And then again, just like all of our other ones, we can subtract a from both sides to get our factor of bx minus a. All right, so the first thing that we're going to go ahead and start with is we're going to go ahead and be given zeros, and we want to use this in order to write our polynomial in factored form. All right, if we start with example A, we have zeros of 11 over 2 and 7. So what we can do is we can go ahead and say, okay, this is my first 0, 11 over 2. And I can rewrite this as a factor of x minus 11 over 2. You can do that. Or you can also do what we talked about just a second ago, is if you don't want to work with fractions, what we can do is we can take this denominator and we can make it the coefficient. And so we can also write this as 2x minus 11. All right, we also have a 0 of 7. And so we can write this as a factor as x minus 7. In either case. Okay, now one of the reasons that I do like to try to write things without fractions is because right now, for my second version, we can go ahead and say just f of x equals 2x minus 11 times x minus 7. Unfortunately, in the first one, we can't do that. What we need to do is, I need a leading coefficient of 2. And so we need to add that into our function. And we can go ahead and take it, whatever the leading coefficient is, it's still going to be the leading coefficient when we write this in factored form. All right, we do want it as a function, and since I didn't leave enough room, I'm going to go ahead and say equals f of x on the other side. And that's all we're doing here. Notice that in the top example, we can also get down to the bottom example. If we distribute the 2, we do get our 2x. And if we distribute the 2 to the minus 11 over 2, the denominator cancels, leaving us with the minus 11. All right, let's look at a couple more. All right, let's come to example B. Example B, we have zeros of -1 and 2. If we write this in factored form, x equals -1 becomes the factor of x plus 1. And x plus 2 becomes a factor of x minus 2. The last thing that we need is we do need our leading coefficient. It should stay the same. And so because we don't have any fractions running around, we do need to go ahead and bring our coefficient, our leading coefficient, down from the original function, and we're just going to put it outside of our factors. All right, we set this equal to f of x, and we're done. Now, these two particular examples are examples that, we could have found our zeros to begin with. These are quadratics, which means that we could have factored and got our zeros, and we would have been fine, okay? Now, as we get into more complicated polynomials, starting with cubics and quartics and everything else, it does get a little hard unless we have a special setup. Let's come down to example C, and let's do one more. Example C, we have 7x cubed minus 21x squared minus 7x plus 21. All right, we have our zeros. We have a 0 of -1. We have a 0 of 1. And we have a 0 of 3. All right, so for each one of these, we're going to go ahead and change them into factors. X equals -1. When we write it as a factor, we're going to write it as x plus 1. We change the sign of the number. X equals 1 becomes a factor of x minus 1. And x equals 3 becomes a factor of x minus 3. The last thing we need is we need our leading coefficient. It was 7 in our original problem, and it is going to stay a 7 in our factored form. All right, that takes care of that. We're going to do one more thing in this presentation. All right, the last thing that we're going to do in this section is we're going to talk about finding real zeros algebraically. And so when we do this, we do want to go ahead and keep in mind all of our techniques that we've talked about so far this semester and in previous math classes. We want to start with our factoring tools. We always want to check if we can factor out a GCF. If there are 4 terms, we want to try factor by grouping. And one thing to note is we are only interested in real solutions. If we have any non-real complex solutions, we're going to go ahead and discard them. Other techniques that we do want to consider is square root property. We might see some of that running around. And quadratic formula. Now remember that square root property and quadratic formula, these can only be used if it is a quadratic. If we are starting with a cubic or a fourth degree, then we do need to start by factoring it into smaller things. All right, let's go ahead and start with example A. Example A, we have x cubed plus x squared minus 6. We want to go ahead and start by factoring this. And so for this one, we do have a greatest common factor. All of these have at least one x. So we're going to go ahead and factor that out. And if we take an x away from each term, what we are left with is x squared plus x minus 6 equals 0. All right, we can factor further. And if we factor this further, we have x squared breaks down to x and x. Things that multiply to 6 are 2 and 3. Because it is a minus 6, I do want different signs. And I want my larger thing to be positive. And so this is going to be plus 3 and minus 2. From here, we can go ahead and set each factor equal to 0. And so we get x equals 0. If we set x minus 2 equal to 0 and solve, we do get x equals 2. Remember that the numbers for our zeros and our factors are going to be opposites. So if we have a factor of x minus 2, we can go ahead and say we have a 0 of x equals 2. And then finally, we have x equals negative 3. Same thing. Our factor and our 0 have different signs. And we're done. All right, our next example, we have 4x to the 4th plus 7x squared minus 2. We are going to start with our factoring techniques. And even though it's not a quadratic, we can still use the same techniques we use for factoring quadratics. The main difference here is that when we factor this, we're going to do x squared and x squared. All right, for my numbers that multiply to 4, you can go with 2 and 2, or you can go with 4 and 1. We don't want to go with 2 and 2, only because I do have that middle number is odd. And if we multiply numbers by even numbers, we always get even numbers. And if we combine even numbers, we end up with an even number. And so the only way that we're going to break down 4 is 4 and 1, or 4x squared and x squared. We have 2. Things that multiply to 2 is 1 and 2. I cannot put the 2 in the same set as the 4 because they have a common factor. All right, and then from here, we want to go ahead and figure out our signs. We have that we are multiplying to a negative 2, which means that I have different signs. And I want my larger quantity to be positive. In order for that to happen, we want a plus with our 2 because we get 8x squared. And then we're going to go minus 1. And 8x squared minus x squared is going to be 7x squared. All right, from here, we can go ahead and set each one of these factors equal to 0. And we can solve. You can do this using factoring again. The first one is difference of squares. Or we can also use square root property, because everything here is squares. And so if we do square root property, we get 4x squared equals 1. We can divide by 4. We get x squared equals 1/4. And when we take the square root of both sides, we get x equals, remember, plus and minus, and the square root of the numerator is 1, square root of the denominator is 2. All right, for our second factor, if we subtract 2 from both sides, we get x squared equals -2. And you can continue if you want, but remember, we're in the real number system, and so these are not real. And so we cannot take the square root of a negative number in the real number system, and so we are done. Our only answers are going to be plus and minus 1/2. All right, let's try 2 more. All right, our next example, we have 2x cubed plus 4 equals x times x plus 8. The first thing that we want to do is we want to get rid of the parentheses. We want to move everything to one side of the equation. So we're going to start with our 2x cubed plus 4. I'm going to distribute the x, and we get x squared plus 8x. We're going to move everything to the left side. And I want to write this in descending order. So if we do this, we get 2x cubed minus x squared minus 8x, and then finally our plus 4. All right, we have 4 terms here, and 4 terms always is usually a factor by grouping. So we're going to start by grouping our first 2 terms together. I can factor out x squared. And if we get rid of x squared in each term, we're going to be left with 2x minus 1. All right, if we go to the last 2 terms, both of these have a 4, and I'm also going to factor out the negative. And if we divide each term by -4, we get positive 2x minus 1. Our next step in our factor by grouping is we're going to go ahead and factor out the common binomial. And so we get 2x minus 1 in front. And in the first thing, if we get rid of 2x minus 1, we are left with x squared. And in the second thing, if we get rid of 2x minus 1, we are left with minus 4. All right. This is factored, and so we can either continue factoring the x squared minus 4, or you can use square root property. I'm going to go ahead and factor this one. This is difference of squares, and so this is x and x. 4 breaks down to 2 and 2, and we do have different signs. And so what we get is 2x minus 1, x minus 2, and x plus 2. All right, when we set each factor equal to 0, the first one, we're going to add 1 to both sides and divide by 2, which would get a 1/2. The second one, if we set it equal to 0, we're going to add 2 to both sides, and we get x equals 2. And the last one, if we set x plus 2 equal to 0, we're going to subtract 2, and we get x equals -2. And we're done. All right, last one. We have x squared x to the fourth minus 16x squared plus 63. This is going to be kind of like example B. We're going to start by factoring this. X to the fourth, that breaks down to x squared and x squared. Things that multiply to 63 is 7 and 9, and they do combine to 16. For this one, we do have that since this is a positive 63, we want same signs, and we want them both to be negative. And so we should get minus 7 and minus 9. Now, x squared minus 7 does not factor further. And so for both of these, I'm going to go ahead and use square root property. If we do go ahead and set each one of these factors equal to 0, in the first one, we can add 7 to both sides. We can take the square root, and we get x equals plus or minus the square root of 7. Though it is not a nice number, it is a real number, and so we are going to keep this. Similarly for the other one, we want to add 9 to both sides. We're going to take our square root, and we get x equals plus or minus, and the square root of 9 is 3. Notice that we did not do any quadratic formula. That's always an option. But most of the ones that we are going to see here, we are going to either get it down to difference of squares or something that we can use square root property. Okay. Now, when you get into future math classes, then you might get the more complicated versions. But at the moment, we do not have the tools in order to solve some of those more complicated examples. All right, that takes care of this section. And so in the next section, and I believe that's going to finish up our discussion of polynomials. In the next section, we're going to go ahead and talk about rational functions, which we are going to be seeing a lot of new material in there. All right, I will see you guys again soon. And good luck with this section.